So hello everyone, we are the group 9 and we choose 3 papers that focus on Kubernetes. As a refresh, this is a system that is used to automate the deployment, the scaling, and the management of applications in containers. So how does it work? Well, in a few words, the clusters are organized according to a YAML file declaration, which is known as deployment. Nodes are then selected and the container image are propagated in pods. The following papers will refer to the positive points of the Kubernetes and how to tweak the system for better results.
So, starting with the first paper, its title is Autoscaling a Defense Application Across the Cloud Using Docker and Kubernetes. This was released in 2018. In this paper, the authors present Athena, an application with a focus on addressing the needs and demands of the helicopter training continuum at the Australian Defence Forces, investigating its auto-scaling solutions. The goal is to make Athena a cloud-native application with the ability to scale these simulations in real time across the cloud. Okay, so this is what Athena looks like. At the top, we have a Sankey diagram. On the left, enter the trainees or recruits. They go through their career, passing or failing the tests. And at the end is the different careers that they can have. This problem is a bit computationally expensive. One of the reasons is because there is a limited resource of the end structures. And also at the bottom of this image, we see there is a graph that shows the statistics of the amount of trainees and instructors at a given time. To relieve a little bit of the problem of being computationally expensive, they used a master worker remote execution system for high performance. But this was still not enough. So why do we need to scale Athena? It was already suitable for vertically scalable setup, but more organizations within the ADF, for example, the Navy and the Army, showed interest in the system, so it needed to be also horizontally scalable. So we needed to have a flexible infrastructure. If Athena was deployed on the Nectar Research Cloud, which provides an infrastructure as a service platform. It uses a container-based approach, focused predominantly around the Docker technology. It was first deployed into a single virtual machine instance. Again, this only made it vertically scalable. But we needed to also focus on the horizontal scaling. Then they decided to separate the stack into stateful and stateless components. The components were then built into Docker images and run as containers using a pool of worker nodes. This allowed the more database nodes to be supported. Again, this made it into being able to have more simulations. This is what the structure looked like on the cloud. We have Kubernetes, which was used so that the virtual machine instance creation, configuration, and activation can be closer to real time. And then we have Prometheus, which is used to pull the information needed and create custom metrics. These metrics were used so that in Athena, we can sort of estimate when we will have a load of data and can create more virtual machines. So the authors then talked about this algorithm, horizontal pod autoscaler. The first version only based on observed CPU utilization memory usage, but then they evaluate the one that we see on the screen. The autoscaler doesn't react immediately to user spikes. We can see a number 5 that a scale up can only happen if something happens in the last 3 minutes, and number 6, a scale down will wait for 5 minutes. This way, this algorithm prevents rapid execution of conflict of decisions. So to end, the authors only showed some simulations that they did in 10, 20, and 30 years using the algorithm that I showed previously. We can see in this image the number of HPA replicas sort of occur at the same time that there is a CPU burst in the API CPU and the pod CPU. So the authors just say at the end that CPU utilization is not good for auto scaling, that we need to have some other metrics, and they talk about our Kubernetes, since they have these metrics, were able to create a system that resolved the problem that we were trying to talk about.
Oh, guys. Also, my paper also talks about a solution to better Kubernetes, as my colleagues already mentioned. Not only on my colleague Sophia's paper, but also my colleague Manuel already told about on the introduction. Pretty much this paper talks about a way of trying to auto scale for fog computing, which is a little bit different from cloud computing, and that's why they do it as well. I'll talk about it in a bit of a second. Fog computing is, for the ones that don't know, is pretty much a cloud for the IoT devices, as shown here on the image as well. Pretty much is like a different type of cloud because it's IoT applications and devices. It's a bit different of the way you do your normal applications. And with that said, they had to create this paradigm. It's more that's more labored or made for IoT devices. The Kubernetes, like I already mentioned, they tried to do a better version of Kubernetes. They tried to for fog computing because they thought it wasn't like good enough, the Kubernetes version for fog computing. And with that said, they tried to use the REST API server on a master node, as you can see here, pretty much is a Kubernetes cluster for the ones that don't remember. They have the REST API server on the master node, and they have the kubelet. Pretty much it's a connection from the REST API server and the kubelet, and in between, the authors tried to put a algorithm called AES broker. It's pretty much in the middle, sort of here in this range right here, between the API server and the kubelet, and to try to bypass the load status reported by the kubelet. It's pretty much the AES broker tries to do is tries to calculate the way of the CPU usage and memory usage, as Kubernetes also does, but tries to do it in a better way, at least as the paper shows, and we'll see that in a second in the results. It does a little bit better most of the times, but it has some problems here or there, but it's not a big of an issue, because as the authors also mentioned, like, it's not a big issue. It wasn't, at least in the graphs, we can see that big of a difference to say, oh, you shouldn't use AES broker compared to Kubernetes. And I'll see that in a second. Pretty much, as you can see here, they had two graphs. They tried to do arrival rate. They use the arrival rate of the pods. The pods, no, sorry, the applications. Yeah, the pods, exactly. They tried to see how much how much of them went there, and as you can see here, the probability is pretty low with like 5 of the arrival rate. At 5, they pretty much it doesn't like almost get there. With only 1 of the arrival rate. By the way, arrival rate pretty much the amount of requests that goes into the Kubernetes, because for the ones that don't remember of our class on Kubernetes, pretty much the server tries to get the program, whatever application, tries to put it in the node, and pretty much that's a request. Pretty much they try to the node tries to request, and pretty much the server gives it to them. So pretty much I know the time is pretty much 1 divided by the arrival rate, as also mentioned in the paper. And as you can see here, pretty much the cumulative probability of getting there is bigger and bigger with only 1 of arrival rate compared to this, as you can see. Pretty much it's with 5 of arrival rate, it takes a big dive. Not a dive, sorry. It goes up pretty much exponentially to 0.7 with almost like 7 something pods, and from there it just goes to 1. as you can see here, it's pretty much more gradual with only one, but with like 5, it just goes up like in 7 pretty much. So with that said, also as you can see here, and this is wrong on the PowerPoint, sorry about that. Pretty much this also tries to compare the application response time without ASS broker and with AS broker. Pretty much the times of this one over here, much the times from the API server to the kubelet, and so on and so forth. And with AS broker, as you can see, pretty much here, there's only one shot at almost like 300 something seconds at the AS broker. Is worse. But most of it's pretty much probably a place. It depends on the application, as I saw on the paper as well. But like it most of the times goes like it's better to use AS broker than not use it for fog computing, of course. One thing I also want to mention: they try to publish the AS broker for like to use in the fog paradigm, but there's still not. At least I couldn't find any answers on it. So they pretty much try to publish it, and at least for the findings, it seems pretty good. So with that said, it makes sense to keep it up.
Third and last paper is this huge title, Key Influencing Factors of the Kubernetes Autoscaler for Computing Intensive Microservice Native Cloud-Based Application. So the author designated 3 key factors that imply a few tweaks to the algorithm in order to improve the Kubernetes system. The Kubernetes autoscaling approach is a control loop algorithm. It can increase or decrease the number of containers, and in order to make sure it can increase or decrease the number of containers in order to make sure the average CPU utilization is at the target value of 18%. So looking at the first key factor, we have the conservative constant that refers to a problem that can happen, that is a minor fluctuations in the workload density might lead to frequent unnecessary automated changes in the cluster size. So the solution is to use this constant with a value between 0 and 10%. So this way, the autoscaling method won't terminate or create new instances that will result in an unstable situation. The second factor is the CLTP. The problem is that a short time between successive adaptation actions can lead to bad decisions, automated decisions. So by raising the CLTP, which should be longer than starting up a new container instance, the adaptation decision will be made while the system is stable. The authors also refer to that under predictable bursting workload scenarios, various CLTP intervals should be considered. So the third and last factor is stopping at most one container in each CLTP. This is because the standard Kubernetes autoscaling algorithm may fail to provide an expected application performance during on and off workloads. And so by restricting the method to only terminate at most one container instance in each adaptation, we solve this problem. The 3 factors were tested with different values, and each factor was tested in a different workload. So the first factor was the conservative constant. It was used in a predictable bursting workload scenario, and with a value of 5, it offered the fastest average response time and the best resources utilization. The second factor was tested in an unpredictable bursting workload scenario. Of course, it was also predictable since they were the ones who made it unpredictable. And the default for Kubernetes Autoscaler proved to be the best, even though the other 2 intervals offered benefits, but only in certain moments. The last factor, it proved to be that the second strategy at stopping at most one container in each CLTP is the best, that offers a faster average response time and allocated more microservices on average.
So to conclude, reading all these 3 papers, Kubernetes is a really good tool to use when autoscaling is the necessary for the system that we are designing. And the last paper show there is still a way to grow, and there is always ways to get better results from this system.